Welcome to The Explainer. Today, we're going to crack the code on a pattern that is, and I'm not exaggerating here, almost everywhere. It shapes our world in ways you might not even realize, from the heights of people in a crowd to the scores on an exam. It's called the normal distribution, and honestly, it's one of the most powerful and fundamental ideas in all of statistics.
All right, so here's our game plan for today. First, we're going to uncover the secret behind the famous bell curve. Then we'll pop the hood and really dig into the formula that creates it. After that, I'll show you a super powerful shortcut called the Z-score, and we'll use it to solve a real practical problem. And finally, we'll connect all the dots and see why understanding this one single concept is an absolute game changer for anyone who ever looks at data.
Okay, let's jump right in with the big mystery. You've definitely seen this shape before, the bell curve. But what you might not realize is just how incredibly often it shows up in the world around us. It's almost like a hidden blueprint that connects things that, on the surface, seem totally random.
It is a fantastic question. And I mean, really think about it for a second. If you take the time to measure the heights of thousands and thousands of people, or you plot out all the scores from a major exam, or maybe you even track the tiny errors a machine makes when it's filling soda bottles, something amazing starts to happen. The data begins to organize itself into a pattern. Most of the values you'll see cluster right around the average, and as you move further away from that average, either higher or lower, the values get less and less common. They all fall into that same beautiful symmetrical bell shape.
You know, calling it the mother of all distributions really isn't an exaggeration. Think of it like this. In data analysis, when you get a brand new data set and you have absolutely no idea what pattern it follows, the normal distribution is your best, safest, first guess. Now, why is that? Well, it's because so many processes, both in nature and things we've created, are the result of many small, random factors all adding up. A person's height, for instance, isn't determined by just one single thing. It's the result of countless genetic and environmental factors all contributing a little bit. And the sum of all those little random influences is what creates this pattern. It's the default, the foundation upon which so many other statistical tools are built. Understanding it isn't just helpful, it's non-negotiable.
So let's really unpack that official definition. The word continuous just means the data can take on any value within a range, not just whole numbers. Think about height or temperature. You can be 175 centimeters tall, or 175.1, or 175.11, and so on. There are infinite possibilities. Symmetrical about the mean is exactly what it sounds like. If you were to draw a line right down the middle, at the average, the two halves would be perfect mirror images of each other. And the central idea, the real heart of it, is just elegantly simple. The closer a value is to the average, the more likely you are to see it.
Okay, so now for the fun part. It's time to look under the hood. Every single one of these perfect bell curves, no matter how tall or wide, is generated by a single, powerful mathematical formula. Now, it might look a little intimidating at first glance, but we're about to see that it's really just built on two surprisingly simple controls.
Okay, here it is in all its glory, the normal probability density function. I know, it looks like a beast. But please, don't be scared off by all the symbols. The best way to think of this is as a machine, and this formula is the blueprint for that machine. Now, the amazing thing is, we only have two dials we can actually turn to control it. Those are the Greek letters mu, which stands for the mean or average, and sigma, which is the standard deviation. Everything else you see here, the e, the pi, those are just mathematical constants. They're locked in place to make sure the machine works right. That whole first part, 1 over square root of 2 pi, that's just a scaling factor. Its only job is to make sure the total area under the curve always adds up to exactly 1 or 100%. The real magic happens in the exponent, that part attached to the e. That's the engine of the formula, and notice what's at its heart, x minus mu over sigma. This little piece is constantly measuring how far any given point x is from the average. The rest of the formula just uses that distance to draw the perfect bell shape. But the power to change the curve, that lies completely in mu and sigma.
And this is where it all just clicks into place. Those two symbols, mu and sigma, are the only two controls you will ever need. Think of mu, the mean, as the location dial. You turn it up, and the whole curve just slides to the right on the number line. You turn it down, it slides to the left. It does nothing more than set the center of your data. Then you have sigma, the standard deviation. This is your spread dial. If you have a really small sigma, it means your data is all tightly packed together, giving you a tall, skinny curve. If you have a large sigma, it means your data is much more spread out, and that results in a shorter, wider curve. And that's it. Seriously. Every single normal distribution you will ever encounter in your life is just some combination of a setting for the location dial and a setting for the spread dial.
And those two simple controls give rise to all these beautiful, predictable properties. We already know it's bell-shaped and perfectly symmetrical. Now, because of that perfect symmetry, something really cool happens. The mean, the average, the median, the middle value, and the mode, the most frequent value, are all the exact same number sitting right there at the peak of the curve. Here's another interesting detail. See the tails of the curve? They never actually touch the bottom axis. They get closer and closer, but they stretch out to infinity in both directions. This is important because it mathematically accounts for the possibility of extremely rare outlier events. And finally, as we mentioned, if you were to measure the total area underneath that entire curve, from negative infinity to positive infinity, it would always add up to exactly 1, which represents 100% of all possible outcomes.
Okay, so we've established we have this incredibly powerful tool. But, and you know there's always a but, this power also creates a brand new problem. Since you can have a normal distribution with any mean and any standard deviation, that means there are literally an infinite number of possible bell curves out there. So the big question becomes, how on earth do we compare a value from one of these curves to a value from a completely different one?
Exactly. This is the classic apples and oranges problem. Imagine, you get a score of 200 on a test where the class average, the mean, was 100 and the standard deviation was 50. You feel pretty good. Then, on a different test, maybe a really hard one, you get a 12. But on that test, the average was only 8 and the standard deviation was 2. So, which performance was actually better? You can't just compare the raw scores of 212. They're on completely different scales. It's meaningless. We need some kind of universal translator.
And that is where the standardized normal distribution comes into the picture. Think of it as our universal benchmark, our Rosetta Stone for statistics. It's a very special, specific version of the normal curve where we've locked the dials. The mean is always set to 0, and the standard deviation is always set to 1. By converting our apples and our oranges onto this one single standard scale, we can finally compare them in a fair and meaningful way.
And this simple, elegant little formula is our universal translator. This is how we get everything onto that standard scale. Let's walk through it. First, you take your specific value, your score, which is x. You subtract the mean of its distribution, mu. That gives you the raw distance from the average. But the key step is next. You divide that difference by the standard deviation, sigma. What you're doing is rescaling that distance. You're no longer measuring in points or inches. You're measuring in units of standard deviations. The result, z, is what we call a z-score, and it's incredibly powerful. It tells you exactly how many standard deviations your value is from its mean. A z-score of +2 means you're 2 standard deviations above the average. A z-score of -1 means you're 1 standard deviation below average. It's the ultimate equalizer.
So, now that we have our universal translator, the z-score, let's actually put it to work. We're going to walk through a real-world example, step by step, to see how we can go from a simple question to a precise probability, all without having to touch any scary, complicated calculus.
The whole process is really just a simple 3-step recipe. It's super straightforward. First, you state your problem clearly and you identify your key ingredients. What's the mean, what's the standard deviation, and what's the specific value x that you're curious about. Second, you use that handy formula to translate your x value into a z-score. And third, this is where the magic happens. We get to use a major shortcut. We skip all the hard math and simply look up our z-score in a special chart called a z-table to find our probability.
Okay, let's get our hands dirty with a real problem. Let's imagine a website's image download times are normally distributed. On average, it takes 8 seconds, that's our mu, and the standard deviation is 5 seconds, that's our sigma. The question we want to answer is, what is the probability that any given download will take less than 8.6 seconds? So if we were looking at the bell curve, we're trying to find the size of the area under the curve all the way from the far left tail up to the 8.6 second mark.
Step 2, let's translate this into our universal language. We just plug our numbers right into the z-score formula. Z equals our value, 8.6, minus the mean, 8, and we take that whole thing and divide it by the standard deviation, which is 5. So that gives us 0.6 divided by 5, which equals a z-score of 0.12. So what does the z-score of 0.12 actually tell us? It means that a download time of 8.6 seconds is just a little bit, specifically 0.12 standard deviations above the average download time. It's pretty close to the middle.
And now for step 3, the shortcut. We take our z-score, 0.12, and we go to a z-table. Now, if you've never seen one of these, here's how it works. You look down the left-hand column to find the first part of your score, which for us is 0.1. Then you look across the top row to find the second decimal place, which is 0.02.
The number where that row and that column meet, in this case 0.5478, that's our answer. That number represents the total cumulative area under the standard curve to the left of our z-score.
And just like that, there's our answer. The probability of an image downloading in less than 8.6 seconds is 0.5478, or, if you prefer, 54.78%. We just went from a practical, real-world question to a precise statistical answer. And all it took was a tiny bit of algebra and looking up a number in a table. No calculus needed. Pretty cool, right?
So, we have covered the what, and we have covered the how. But the most important question is still hanging out there. Why? Why does all of this matter? Why did we go through all of that? Well, because the concept of the normal distribution isn't just some statistical curiosity. It's a critical checkpoint, a gatekeeper for pretty much any kind of serious data analysis.
Here's the bottom line, and this is really important. Normality is a gatekeeper. Many of the most powerful and common tools in a data analyst's toolbox, things like t-tests, ANOVA, linear regression, they all come with a very important warning label that basically says this tool works correctly only if your data is normally distributed. It is a fundamental assumption. That's why one of the very first things a good data scientist does when they get a new data set is check it for normality. If you skip that step and you use a tool that assumes normality on data that isn't normal, your results won't just be a little bit off. They could be completely wrong, leading you to make bad decisions based on flawed conclusions.
And that brings us to one of the most useful, practical rules of thumb in all of statistics, the empirical rule. You might also hear it called the 68-95-99.7 rule. For any normal distribution, no matter what its mean or standard deviation is, you can be confident that roughly 68% of your data will fall within one standard deviation of the mean. About 95% will be within two standard deviations, and a massive 99.7%, almost everybody, will be within three. This is an incredibly powerful mental shortcut for quickly getting a feel for the spread of your data and for spotting potential outliers. If you see a data point that's more than 3 standard deviations away from the mean, you know you're looking at an extremely rare event.
So, our journey today has taken us from seeing a hidden pattern that's all around us to digging into the math that actually drives it, to learning the universal language of the z-score that unlocks its power. The normal distribution isn't just some abstract curve on a graph in a textbook. It's a fundamental blueprint for how so much of our world works. And now that you know how to read that blueprint, the only question left is, where are you going to see it next?